Next, we have Vivek from UC Berkeley, who would be talking about the privacy risks of adversarial VR game design.
All right, hello everyone. My name is Vivek Nair. I'm going to be talking to you today about privacy in the metaverse. This work is also co-authored by Gonzalo from TU Munich and our two advisors, Professor Don Song and Professor James O'Brien in UC Berkeley. And I'll also quickly acknowledge NSF, NPSC, Hertz Foundation, and Berkeley RDI. So when I use the term metaverse, this is a subject of a lot of hype recently, and it's a term that has come to mean many different things. In this talk, when I say metaverse, all I'm talking about is extended reality devices, and in particular, sort of multi-user experiences within these extended reality devices. So more than one user interacting in some kind of virtual environment through the use of immersive technology. And you might have heard of the recent Apple announcement of the Vision Pro headset. There's a lot of big tech companies investing heavily in this area recently. And so understanding the privacy consequences of these types of experiences is becoming increasingly important. But I realize that there's not a lot of general familiarity, so I'll start with a brief overview of how these platforms tend to work. Basically, it all starts with some sort of extended reality device, which is typically a head-mounted display, and then some kind of hand tracking or handheld controllers. And that device is streaming telemetry data, which is basically the head and hand motion or body motion data of the user, to some application software. And that software can be running on the device or on an attached computer. And it's basically using the motion of the user to render frames, so to render audio and visual stimuli for the user that is then fed back through the device. But if it's a metaverse or multi-user experience, then that same motion data is going to be fed to a server somewhere in the cloud and then on to other users around the world. And this is fundamentally how metaverse systems work, right? So your device is generating a stream of information about you and then sending that off to all the other users who are in the same virtual world so that they can see an avatar representation of you on their device. And so this is, should already raise some flags for privacy practitioners, because we see that the core technology or the core information flow that's fundamental to this technology involves sort of a real-time stream of data from our device to all the other users' devices. And so we consider each of these 4 steps in the information flow to be potential adversaries. And this is a fairly standard threat model nowadays in metaverse security and privacy research. So each of these entities, whether it's the device, the software, the remote server, or even the other users, are all seeing the same information, which is your head and hand motion, maybe eye tracking, and so on. And so they all could potentially use that information to make inferences about you. Now, almost all of the research in this field so far has focused on these last 2 adversaries, the server and the other users around the world. And this makes a lot of sense, right? Because these are sort of the most remote adversaries. It's very hard to audit what a server is doing with your data, let alone what all the other users are doing with your data. But they're also quite passive, right? So I'll give you some examples. Our lab, RDI, has published some related works looking at these 2 adversaries. We had a study in Usenix, which basically just passively observes users playing a rhythm game called Beat Saber. and just from their head and hand motion tries to uniquely identify them. So it tries to learn which user they are based on their unique motion patterns. And it turns out you can do this at a rate of about 1 in 50,000 or more. So it's in fact comparable to something like a fingerprint scan. That's how unique and consistent your head and hand motion patterns are. And we followed this up with another study, which is currently in ISMAR, and that is going further, trying to learn information about you, like your demographics and so on, just based on your head and hand motion patterns. And it turns out you can also do that to a significant extent. But all of these, again, are sort of passive attacks, right? What can we do if we just watch this data stream coming from your device and then start trying to make inferences based on it? Right? And it turns out that not much research at all has focused on this adversary, the application itself. And so the question we try to answer with this study is basically, if we focus on the application that is actually delivering the frames, delivering the immersive experience to the user, what kind of further adversarial capabilities do we gain by sort of having control of that virtual immersive environment? To answer this question, we designed a game, a VR game called Metadata, and it's kind of an escape room style game. If any of you have played these escape rooms where you basically solve a bunch of puzzles and you're trying to go from one room to the next. We built something like this in VR, and we invited 50 participants to come into our VR lab and try out the game. But behind the scenes, we had actually designed this game in a very adversarial way. So almost every puzzle, almost every room in this game is designed to trick users into revealing information about themselves. Other than general consent to learn whatever information we can find, users didn't know what specific attributes we were looking for until the end of the study. And so to them, it just looks like an ordinary escape room game, and they're just instructed to go through the game and perform to the best of their abilities. And ideally, they wouldn't even know what's going on. And what we found in the process of designing this is that once you have this active adversarial capability, the attacks that are possible in VR are dramatically exaggerated. And so there's a lot of things that you can do once you design the game that you can't observe just through passive motion. I'll give you a very simple example to start off. So one of the most uniquely identifiable static anthropometric measurements is wingspan, right? So it's actually second only to height in how consistently you can identify an adult based on this anthropometric. And the problem with just a static posture is that it's very hard to measure someone's wingspan precisely when they're standing in a natural pose. So if you are a passive adversary, you can try to watch someone for hours in VR until they happen to go like this and show you their wingspan. But if you're an active adversary, you control the game, suddenly you just need to design a mini game within your environment that tricks users into placing their hands out to the side. In our case, we developed this mechanism where users basically have to mimic the poses on the wall, and they reveal letters by doing that. And one of the poses like this, and suddenly you know their exact wingspan. You get a very precise measurement. So I mentioned this not because wingspan is a particularly pernicious attack, but because it's a very clear example of how an active adversary who's controlling the environment can immediately get users to reveal a data point that they would otherwise not have necessarily revealed. Another good example of this is reaction time, right? So again, you can sort of passively observe someone's interactions with the world and try to, maybe there's a sound and how quickly do they flinch, so you might eventually get some measure of reaction time. Or if you control the application, maybe you just design a button that someone needs to press as quickly as possible when something changes colors. Well, now you have a very precise measure of their reaction time. And I should point out with a lot of these that it's not just about what you're directly measuring, right? It's equally important to imagine all of these sensitive attributes that are correlated to these things. In the example of reaction time, this is something that's highly correlated to age. And it turns out if you can get a very precise measurement of someone's reaction time, you can make a fairly good guess at their age as well. Other examples of these correlated attributes are things like visual acuity, right? Because you have this head-mounted device, you can get a fairly good measure of someone's general visual acuity by placing a challenge into the virtual environment that people would respond to differently based on their level of visual acuity. Again, this is very hard to measure passively. Just, you can look at hours of this data stream and not really be any closer to measuring someone's vision. You control the application, and you can do this in a natural way. And again, right, strongly correlated to age. Another thing you have the capability to do is watch where someone's looking. And you can do this even without an eye tracking system based on the direction of their head. We did a very simple attack based on this that learns which languages someone speaks based on which words in a room they were appearing to read. But you can imagine, again, more pernicious versions of this that try to learn certain preferences of the user based on where they're looking and what they're interacting with. So these are just a few examples. I can't go through all of the rooms. There were over 20 rooms in this escape room that all is sort of designed to learn different things about the user without really revealing that it's about data collection, trying to look fairly natural. I'll give you one last example here, which is trying to measure the user's physical environment. So this is something you can do, not just the user itself, but if you allow a user to sort of walk around the room and they're wearing this motion capture setup essentially, and then you also get a fairly good way to measure the size and shape of the room that they're in. And again, this is something that an active adversary can do much better. So in our case, what we did is we sort of hid objects in different corners of the virtual room, and this encourages users to walk all around their physical room in order to find these hidden objects. And now we have a very good map, essentially, of the room that they're standing in, rather than just waiting until they maybe happen to walk around. So these are all examples that hopefully illustrate the point of if I'm trying to learn specific attributes, in VR, I need to consider whether having control of the virtual environment helps me go in that direction. Overall, here's the entire set of attributes that we were able to directly observe from users. So about 20 or so attributes that we can directly observe. Again, I skipped over many of the rooms in the interest of time. One of the things that we did is we actually, in our escape room game, hid the entire MoCA, or Montreal Cognitive Assessment. So we got a very good measure of someone's mental acuity, like if they have dementia and so on as well. And so physical disabilities, mental disabilities, things like that, are clearly inferable to active VR adversaries in a way that passive adversaries might not be able to discern. And then, as I mentioned, right, we need to think not just about the attributes, but all the hidden correlations. So when we look at all of these primary attributes and the raw tracking data and put it into a machine learning model, we can also get a fairly good, actually a very good estimate of someone's demographics. For example, almost perfect inference of the gender of the participants, right? So what this shows, and I'll say that these metrics in accuracy far exceed what the passive observation studies have been able to achieve. So I think the main takeaway here, right, is, and I do think with Apple entering this field, maybe 1 or 2 years from now, hopefully we're going to see a lot more AR and VR focused research in pets. And I think the main takeaway of this study is for anyone who's considering researching the privacy and security implications of AR and VR, don't neglect this passive adversary, right? The active adversary. So, it's very tempting to think of the privacy risks of VR as coming from this vast array of sensors. You have body tracking, you have eye tracking, you have cameras, microphones, LiDAR arrays. That's, of course, part of the equation, but I'm trying to argue that an equally important part of the equation is this super immersive environment that you're putting users in, this immersive audio and visual experience that an adversary can totally control and manipulate the virtual world of the user to reveal information in a way that is totally disanalogous to mobile apps or anything like that. So that's my main takeaway. Thank you for your time, and happy to answer any questions.
So we have some questions online. The first one is, what kind of defense mechanisms do you suggest to prevent these kind of adversarial data collection in VR games?
That's an excellent question. So we've looked at a couple of different defensive approaches. One of them, we have a paper called MetaGuard, which was recently accepted to WIST, and this is a differential privacy-based defense. You can't just put differential privacy, you can't just put noise on all the sensors, because then users get motion sickness, turns out. So what you have to do is you have to leverage this VR-specific property called homuncular flexibility. Basically describes the fact that users are flexible to manipulations in certain dimensions. Like if you make someone have super long arms, it turns out they can just naturally adapt to that. So by adding noise in a targeted way to specific dimensions in a differentially private way, this turns out to be one pretty good way to defend against inferences. And then we're also looking at things like machine learning-based defenses.
Another question is, I guess you debriefed participants after the experiments. Do you have insights into how they perceived all these different possibilities for tracking?
Yeah, that's a great question. So, for ethics reasons, we basically told participants, hey, we are trying to learn information about you, but we didn't tell them exactly which information, just the categories like biometrics, demographics. And then we said, hey, after the study, part of our debrief, before revealing the set of attributes, and then there's an opt-out procedure, but before revealing, we sort of asked them, do you have any idea which attributes are being collected? Now, it's a bit of an unfair question because there's like 25 attributes being collected, but users at most were able to name one or two things, and these were things that we probably could have done a better job of disguising. Things like a visual test, which clearly looked like a visual test still in the game, but which an experienced developer would have been able to hide better, most likely. So the short answer is no, users weren't able to detect the vast majority of the attacks that were happening.
There are a few more questions, but let's stop here and thank the speaker.
Thank you.